And in this video, we are going to investigate a few special properties of dot products. And once we have a clear understanding of these properties, they will carry into the later problems regarding dot product. And so the first and the easiest understanding. Now, remember back in the world of scalar multiplication, back in the world of just numbers multiplied with numbers, how about just real numbers multiplied with each other? 2 times 3 is the same as 3 times 2. So this property we used to know that as the commutative property. So, but keep in mind, dot product that we define here is a completely brand new way of taking a product, of taking a multiplication. It's a multiplication between vectors. So do not just assume, a vector u dot v is going to be the same as the vector v dot u. We have to investigate that carefully. So let's find out. So let's say I have and for most of our demonstration here, I am going to use, I am going to stay in the R2 vectors. However, like I said, we can always extend these proofs, these illustrations into vectors in Rn. And so let's say we have a vector u being in R2 with components u1, u2, and another vector v having components v1, v2. So let's find out a generalization right here. But let's start out to simply take the dot products between these two vectors. Definition says, and keep in mind right now I'm starting out with u in front and v is in the back. So u dot v is the way how it says right now. So the definition coming straight out from the definition, we should be looking at u1 times v1 in the usual multiplication, and then add u2 times v2. But then, so now once we put ourselves, and let's look at this setup right here, we are entirely in the usual multiplications. Then, based on the usual multiplications, u1 times v1 can be the same as v1 times u1, simply because multiplication in real numbers are simply commutative. Plus, that second term becomes v2 times u2. And so now this new setup right here all of a sudden opens up our mind, and hey, wait a minute, we recognize that this is nothing but just v dot u, but slightly different order, the flipped backward version. And so now we recognize that the dot product we just now learned is actually commutative as well. So the first property we recognize, u dot v is going to be the same as v dot u. And so now we can legally say that anytime you take a dot product, you can twist the order around and it's going to give the same result. So this property here is commutative. All right. And so once again, think about back in the days where we were doing, let's say, 2 as a common factor multiplied with 3 plus 5. So what we can do sometimes is that we were able to, and in the world of real numbers, we are able to distribute that common factor 2 into each one of our inside parentheses here. And so we're ending up with 2 times 3 plus 2 times 5. This is nothing but the distributive law. But that was for the usual multiplications in terms of real numbers. Now we are doing vectors multiplication, and in particular the dot product. Will it work the same? Let's say, and once again for simplicity, I'm doing all these proofs and demonstrations based on vectors in R2, but it should work the same way in the other dimensions. So let's say U is a vector in R2 with components U1, U2. V is a vector in R2 again with components V1, V2. And for this work right here, we're going to need a third vector. So how about I'm going to name it W. Is a vector in R2 again with components W1, W2. So what we want to know, what we want to find out is that, let's investigate. I can't just simply start out assuming that U dot with the sum V plus W will be the same as the usual distributive law. So let's investigate, let's find out. So from what we understand so far regarding all the properties of vectors, we know how to take a dot product. We know how to take the sum of two vectors, but we just don't know, we're just not sure whether we can distribute that U as a dot product with V and distribute that U as a dot product with W and add up the two in the usual multiplication. We're not sure about that. And so how about let's do this. So I am going to proceed as adding these two vectors. And so what I have here, let's create a separate space here to work, but V plus W, let's rewrite it. The rule of adding vectors is simply just adding component wise. So V1 plus V2, my apology, V1 plus W1. Second component is V2 plus W2. So this is my representation of the sum vector V plus W. So U dot V plus W turns out to be equals U1 multiplied with V1 plus W1 plus U2 times, and these are just the usual multiplications, times V2 plus W2. So you can pause the video and double check yourself. Alright, so hopefully you double checked. And so in this representation of the dot product between U and V plus W, these are to remind everybody that they are just the usual multiplications. And so we can actually just distribute each one of these terms. So now what we have here in the next line is U1 times V1 plus U1 times W1 plus, and in the next term after distributive law, U2 plus V2 times V2 plus U2 times W2. And what we will do here in the next step, I am going to rearrange these terms here in the following way. I'm going to group U1 V1 together with U2 V2, and I am going to group U1 W1 with U2 W2. So these are all the algebraic techniques we've been learning since a long time ago, but even in a class like this, it's heavily the driving our work right here. But so now if we looking at this first group here carefully, then that first group turns out to be nothing but just the dot product of u, and v. And once again, if we're looking over to this other group right here, it turns out to be nothing but just the dot product between u and w. And so what we came and what exists between the two is the addition. And so now we actually found and we made that connection. So now we discover that dot product is also distributive. Or in other words, distributive law does work with dot product. So it's another important property that we recognized. All right, and at this point, let me introduce to everybody a few theorems, a couple of theorems that's very important regarding the dot products. And at this point, you have seen that, and you have seen how dot products are heavily related to lengths of vectors. As a matter of fact, there are one. So let's look at the first theorem here. Let's look at one theorem here. I'm going to say let u and v be vectors. And this theorem is actually meant for vector in Rn in general. It's not only in R2, not only in R3. It works in Rn. So I'll just get straight to the point here that vector u and v be vectors in Rn. Then this is what we found here. We found out that the dot product between u and v. Now keep in mind, earlier what we learned was the definition of how we find the dot product. But now in that way we recognize a connection here that dot product between u and v turns out to be equals to the length of u times the length of v times with cosine value of theta. So where theta is the angle between u and v. So the statement of the theorem is here, the most important statement in the theorem. And here is just a clarification of where that theta came from. So in any space, you have a vector u, you have a vector v. They will make an angle between them, and that's what theta is for. And so in this case right here, this theorem we just now wrote down is indicating that once you take the dot product of u and v, it turns out equals exactly the length of u times the length of v in the usual multiplication, and multiply with cosine of theta. Doesn't matter if we're looking at vector in R2, vector in R3, and vectors in R higher than 3, even though we can't even imagine anymore how vectors in the higher dimensions is going to look like, but they work similar. So now let's offer the proof. Let's look at the proof to that theorem we just now wrote down right here. And I have to admit, the proof here is more like limited to the vectors in R2 and R3. And then later on, when your mathematics learning has become more advanced outside of this course in algebra, in linear algebra, then the courses there in your higher levels will reinvestigate this exact same theorem again, but to be able to give you that flexibility to prove for vectors in space higher than R3. So now it doesn't matter if you're looking at a vector in R2 or R3, but let's say here's a vector u, and here's a vector v. So in a way, how I'm drawing u and v like this, theta is here, and that's the idea. And by the way, I should have also mentioned that theta is defined to be the angle between. You have learned enough trigonometry that anytime you're drawing two rays or two vectors, you're actually ending up with two angles, right? So with theta here, by default, we're considering the smaller theta, the smaller angle between the two vectors. So here's the thing. So now this vector u has some length, and this vector v also has some length. And so now I'm going to draw a vector like this, pointing this way. It's actually the vector u minus v. Okay. But notice, if we put all the three vectors together and they're already in the exact picture right now, what we have here is a triangle. What we have here is a triangle. And so here's the thing. And of course, now if we're looking at just a geometric figure in its most usual sense, then we have learned back in pre-calculus 2 or trigonometry that the law of cosines. The law of cosine says this length of the triangle, but this length in our learning here is the same as the length u minus v. U minus v is the vector, but now we're looking at the length. The law of cosine says the length of that vector u minus v square must equals to the sum of the length u square plus v square, the length of v square, minus, and here's what I hope many people still remember this, 2 times the length of w, the length of u times the length of v times the cosine of theta. That's what we bring in from trigonometry. Quickly, if you need a reminder, then I can briefly remind everybody, but back in trigonometry, then if this is length A, length B, and length C right here, and the angle theta between A and B, then the law of cosine says C squared equals to A squared plus B squared minus 2AB times cosine of theta. That's what we learned back in trigonometry. And that's how we bring that into this particular proof right here. And so if you're looking at the left-hand side of this equality actually is quite fascinating. So let's look at that left-hand side in particular. I am going to consider the left-hand side. The left-hand side is being u minus v as a vector, but we take the length, the square of that length. So the length of u minus v square, but length of u minus v square, wait a minute, didn't we just learn that it's exactly and nothing but just the vector u minus v dot itself, u minus v. And then carrying on from this step right here, what I can see here, what I recognize is, remember we talked about how dot product can be, how we can apply the distributive law on dot product. And so this consequently gives us u dot u minus u dot v. I would just simply think about the foiling work right here, but we heavily use the distributive law on dot product. So u dot u times u minus u dot v, and then the next one here is going to be v dot u, but with the minus sign, v dot u, and then plus v dot v. So that's what I'm doing to the left-hand side of our, and remind yourself that what we started out with this known facts from trigonometry. And now in this step right here, I'm currently developing out the left-hand side of that equality right there. And so this here gives me, and we've been spending a lot of time learning and hopefully get comfortable with what that concept about u dot u itself. So u dot u itself is, and it's still here in how, that's how we were using it. So anytime a vector dot itself is the same as the length of that vector being squared. And here we have another one here. So length of v square is here. Now we've learned through the special properties of dot products that u dot v is the same as v dot u. So these two terms turn out being like terms. So we can bring them together as a 2 u dot v plus the length of v squared. So that's what we can do with the left-hand side of our equality we brought up earlier. And like I said again, like I remind everybody, this equality came out from trigonometry. So now I'm going to equate. So the left-hand side, which is now finished developing it out, I am going to equate the two sides here, and hopefully my board space is big enough. But so left-hand side is a length of u squared minus 2 times u dot v plus length of v squared. We want to equate that with the right-hand side. So length of u squared plus length of v squared minus 2 times length of u times length of v times cosine of theta. And so equating the two, the left-hand side with the right-hand side, that we didn't do too much to that. What we recognize now, we have opposite terms on the two sides. So the u length of u squared here on both sides can get cancelled out. The length of v squared are opposite terms, or the like term on the, or exact terms on the opposite side. They also get cancelled out. What we consequently ended up with would be minus 2 u dot v, 2 equals minus 2 length of u times length of v times cosine of theta. And so now we can just cancel away the common factor negative 2 in front of each side here, and look at what we have turned out. We now came down to u dot v as a dot product between u and v. Turns out to be, shockingly, length of u times the length of v multiplied with cosine of theta, where theta is the angle between u and v, the smaller angle between u and v. And so we came to the end of our proof right here. And like I said, this proof right here utilized the geometric meaning of vectors. However, I have to admit, its geometric meaning is limited to the vectors only in R2 or R3. And then one day when you advance to a higher course in linear algebra, or a higher course that learns study about vectors, your professors there will represent this proof, but in a much more flexible way, where we break free from the limitation of geometric meaning. And it's still true. So right out from the theorem, then we can conveniently rearrange this relationship as if we're dividing both sides by length of u times length of v, then cosine theta, remind yourself, theta is the smaller angle between the two vectors u and v. So cosine theta can actually be found by u dot v equal over length of u times length of v. And so we gave rise to a convenient formula. So the convenience about that formula we just came up with was that there are times where we have a problem like this. Let's find the angle theta. How about, for simplicity, in degrees? In degrees between the two vectors u equals 2, 1 and v equals 1, 2. So these are the vectors. I don't need to bring up a geometric picture of those, but for sure these two vectors will have an angle between them, whichever the angle that being smaller. So theta is here, u is there, v is here. Okay. We want to find out how big theta is. And so we just now learned that cosine of theta equals u dot v divided by length of u times length of v. And so I am going to spend a little bit time to find the dot product of u and v and the two separate lengths of u and v. And so u dot v equals 2 times 1 plus 1 times 2 equals 4. Length of u equals square root of 2 square plus 1 square, and that equals square root of 5. Length of v equals square root of 1 square plus 2 square, and that's also equals 5. So in this way, cosine of theta will be equals to 4 as the dot product between u and v divided by the length of u being square root 5 times the length of v being square root 5, and this is just the usual multiplication. And so we came to cosine of theta equals 4/5. And so now at this point, I hope you still remember from your trigonometry, but now we have cosine equals to a value, a real value. Then cosine, to find cosine, simply we're going to take the cosine inverse of 4/5. And so in degrees, we should be looking at 36 point in 2 decimals, good enough, 87 degrees, approximately. All right, and now let's look at a couple of important inequalities that famously related or famously came out from the dot product. So the first one I want to introduce here is called a triangle inequality. The triangle inequality says for any two vectors, the length of u plus v will always be less than or equals to the length of u plus the length of v. I don't need to give out a formal proof here for this triangle inequality. However, I can do a quick geometrical explanation of why it's true right there. You can see that the name of this inequality is quite famous. It's called a triangle inequality. So let me now pretend that we're in a triangle. So we have a vector u going this way, a vector v going this way. And so this vector here is the vector u plus v. Okay, but in the end, the figure together is a triangle. And so ever since we were little, we've learned this little theorem. We learned this little truth about any triangle, that in any triangle, the length of one side has to always be less than or equals the sum of the other two sides. Is my statement correct? You take a moment and think about that for me. All right, so I hope you thought through. So how do I bring that statement into this picture over here? Well, right here, what I see is the length of u plus v, but in this picture as a length of a triangle. So the length of u plus v as one edge of my triangle in the picture, it just simply has to be less than or equals to the length, the sum of the other two lengths. The other two lengths are length of u and length of v. And that's why I ended up with the length of u plus v has to be less than or equals to the length of u plus the length of v. And that is why this inequality here is famously referred to as the triangle inequality. Historically speaking, it came out from a triangle. And so now another famous inequality that relates with dot products and vectors and lengths of vectors. The inequality states that the absolute value of the dot product u dot v. Now, so what I'm saying here is we take the dot product, and then the dot product could sometimes be negative, it could be positive. So the dot product in absolute value must be less than or equals to the length of u times the length of v. And I have to clarify that, so here on my left hand side, it's an absolute value because u dot v is a scalar. So scalar could be a negative, scalar could be a positive. So here on the left hand side is an absolute value. The right hand side here are two individual lengths, the length of u and the length of v. This inequality was discovered by Spats. And so to credit this mathematician, we call it Spats inequality. All right. And so here I'm gonna, for this inequality, I am going to give a formal proof right here. There are actually quite a few different ways how people prove prove this inequality here, but some proofs are way too advanced for our level, and some proofs are way too the basics. Here, I'm going to choose a proof. I choose a proof that just right about the level that you guys can understand, and it strictly stays on the definition of dot product, and all that, and bringing in a few understanding about length and angles. All right, so before I give the formal proof, then I need to reinforce a couple understanding. So if you got a vector, then if u with an arrow is a vector, then the length, well, we call it length, but it is a scalar. So hopefully everybody viewing this video at this point agrees with me on that. And as long as we understand that the length of a vector is a scalar, and being a scalar, once again you can multiply the scalar to some other vector. So think about if you have another vector, say v, and you are going to multiply this length of u with v, that is completely legal, and that is a vector. All right, so, and that's just a couple of reinforcement I need to remind everybody. And so here we go. We're gonna start proving that Spats inequality. So once again, formally speaking, before I do any proof, I'm going to restate the statements that we're trying to prove here. But Spats inequality says the absolute value of the dot products between two vectors is always less than or equal to the length of u times the length of v. And so a little bit out of surprise, but here's how I'm starting out with my proof right here. So for this proof, this is what I'm starting out with. So I'm going to say let u and v be vectors. And this proof actually can be generalized for vectors in Rn. In Rn. Then this is what I'm starting out with. I am going to define a vector. I am going to take a dot product between the vector, how about length of u as a scalar multiplied with v, minus the vector length of v as a scalar multiplied with u. So let's look at that vector over here. It's a vector. It's a vector. And the difference of two vectors is another vector. And so if we take the dot product of this vector with itself right here, it does look a little too big for the expression, but basically I'm taking the dot product of the exact same vector. Now, another reinforcement, another little side note here I need to reinforce with everybody as well. I hope you had this understanding in mind, but in case you still didn't realize, and here it comes again, but anytime you take, doesn't matter which vector you're looking at, but anytime you're taking the dot product between a vector and itself, it will always give a value greater than or equal to 0. And so bringing that understanding into our proof currently, this dot product is a dot product between some vector, a vector, and with its own. Then on one hand, we know for sure that this dot product is greater than or equal 0. It's a non-negative quantity. On the other hand, this dot product, now let's do the formula. Now we've learned about distributive law. Let's apply that distributive law here into this problem. So the left hand side here becomes, after distributing terms by term here, first term dot with the first term here gives me a length u times v dot with length of u times v. And then first term and the second term of the other one minus length u times v dot with length v times u. And then now it's these two terms here produce a minus, and now I'm looking at length v times u dot with length u times v. And then I'm running a little bit out of space here, so I'm going to need a little line down here, but I'm going to add. Now these two terms multiply together. That gives me length v times u dot length v times u. All right. And so from the beginning to the end right here, if you're looking at the first term turns out nothing but that first term truly is the two scalar length u and length u here can be put together, can be multiplied together in a scalar as a scalar multiplication, and that becomes a length u square multiplied with what we have here is the dot product between v and v. So here it's another, it becomes another length v square. So the first term here becomes length u square times length v square. These two terms are actually like terms, and we can combine them. They can be combined into minus 2 length u times length v times u dot v. And then the last term here is the same as length v squared times length of u square. And these two terms are now like terms. So we are going to put them as right? So these two combine to become that. And then at this step right here, we can see that all that here that we came down to is greater than or equal to 0, according to the very beginning step. And so what this final inequality here indicates is that we came down to we can add that to the other side right here, and be looking at 2 times length u squared times length v squared is greater than or equal to 2 times length u times length v times u dot v. And then the cancellation of common factors here lead down to having length u on the left hand side times length v, no more square, is greater than or equals to u dot v. But notice, this is not the absolute value version yet. Just keep in mind, what we have right now is length u times length v greater than or equals to u dot v. Then after that, I am going to define another vector. The vector is defined as following: length of u times vector v, but plus the length of v times vector u. Defining that vector, I am going to take the dot product to itself again. And this dot product, since one vector dotting itself, once again should be giving a value being greater than or equal to 0. And then that left hand side, we can do the similar work, distributing out all the terms, and we should run into, after all these steps right here, we should run into a conclusion saying length of u times length of v is indeed greater than or equals to negative u dot v. And so now, putting all that together, the earlier one we've had was length u times length v greater than or equals to the dot product of u dot v. This one here would become, on one hand, u dot v is greater than or equals negative of length of u times length of v, and then this is staying the same. Dot product of u times v is greater than or is less than, if you're putting that on the left hand side, is less than or equals to length of u times length of v, or in other words, u dot v is trapped between one hand is less than or equal to length u times length v. And on the other hand, it's greater than the negative of length u times length v. And all these together, one quantity being trapped between two opposite exact value, then it implies that the absolute value of u dot v has to be less than or equals to length of u times length of v. And that is how we prove the inequality. And the last important property, it's relating about the angles between the two vectors, orthogonality. So two vectors u and v are perpendicular. Anytime or when the dot product u dot v equals 0. Now, it's a new term I'm introducing here, but orthogonality just refers to the fact that when two vectors are perpendicular, and that's what it means. Like that. And so we can quickly see that when they are perpendicular, why are they equal to 0? I mean, why is this dot product equal to 0? Because it doesn't have to be a formal proof, but when two vectors u and v, or this is u, this is v, perpendicular means the angle theta, cosine of theta, has to equal 0. Cosine angle of theta equals 0 means, remember that we've learned cosine theta, as long as theta being the angle between these two vectors, then cosine theta equals 0 means on the left hand side cosine theta equals u dot v times length divided by length u times length v. So that means all that expression here equals 0. The denominator of this expression cannot equal to 0. It's always a positive quantity. So that immediately leads to u dot v has to equal 0.